Almost every picture of the early Earth includes water, but the planet's true infancy had none at all. For its first era, Earth was a barren, searing orb of molten rock, constantly remelted, wrapped in a poisoned atmosphere that made liquid water impossible. A forgotten world still waiting for its very first patch of solid ground. That distant, obliterated past holds a fundamental mystery. What did our planet actually look like before the oceans, and where did the first solid ground come from? To glimpse that vanished world, we have to find clues from an era that left almost no witnesses behind. To answer it, we journey back to Earth's earliest, most violent chapter, the Hadean Eon. This was an epoch so obliterated by time, almost no rock from it survives anywhere on Earth. Yet, from the faintest whispers locked in microscopic crystals, we can begin to reconstruct its alien face. We will trace the planet's fiery birth, confront the profound, still unsolved mystery of how it acquired its water, and witness the contested emergence of the very first fragments of continent from a world of ceaseless geological chaos. This is a detective story where every piece of evidence is fought over and every revelation reveals deeper questions. Our hunt for those foundational clues starts at the very beginning, with the initial formation of this world. That initial formation unfolded around 6 billion years ago, as Earth coalesced from a turbulent disk of gas and dust circling the newborn sun. Countless particles crashed together with ferocious energy, slowly building a protoplanet, and the sheer heat of those ceaseless impacts, amplified by the planet's own internal radioactive decay, melted the growing world completely. It was not a solid sphere, but a searing, incandescent globe of magma, its surface a tumultuous ocean of liquid rock stretching for hundreds of kilometers into its depths. This was the planet's true beginning, a world of elemental fire constantly boiling, venting, and remelting, a place so utterly hostile that nothing we recognize as liquid water could exist on its surface. Yet, even this unimaginable inferno was merely the preface to an even more cataclysmic event. That preface exploded. Around 5 billion years ago, a Mars-sized world, sometimes called Theia, struck the molten Earth in a glancing, colossal collision. The force vaporized much of both bodies, flinging a vast ring of superheated debris into orbit. From that fiery, swirling halo, our moon slowly coalesced. This giant impact hypothesis is the leading explanation for the moon's origin and its unique composition. It also meant any fragile crust or wisps of atmosphere Earth might have gathered were utterly obliterated. The planet was entirely remelted, resetting its surface to a liquid inferno. This cataclysmic event erased almost all trace of Earth's earliest past, making the Hadean Eon a geological blank slate. The planet would have to begin again, even its atmospheric shroud. And the violence did not end with Theia. For hundreds of millions of years afterward, the young Earth was still a shooting gallery. The inner solar system was littered with leftover debris from planet building, and it rained down relentlessly, A barrage that may have intensified into a spasm of impacts, sometimes called the Late Heavy Bombardment. The scars of that era are not on Earth because Earth erased them. They are on the Moon, whose great dark maria are the flooded basins of colossal ancient impacts, still visible to the naked eye tonight. It is one of the strange ironies of planetary science that to study Earth's earliest history, we often have to look anywhere but Earth. The Moon, geologically dead, has held its ancient face frozen for billions of years. Mars, too, preserves vast tracts of terrain older than almost anything on our own restless planet. Earth is the one world in the neighborhood energetic enough to have shredded its own beginnings, alive enough to bury the evidence of how it came alive. Every one of those craters has a missing twin on Earth, scaled up for a larger world. The largest impacts would have been apocalyptic, strikes energetic enough to boil away whole seas and blanket the planet in rock vapor, sterilizing the surface again and again. Whatever gains toward a cooler, wetter world the Earth made, it kept making them in the teeth of a bombardment that could undo them in an afternoon. This is the crucial backdrop to everything that follows. Not a steady march toward habitability, but a brutal, halting negotiation with the sky. That initial atmospheric shroud, however, was a fleeting thing. Captured directly from the solar nebula, this primordial veil was dominated by the lightest gases, primarily hydrogen and helium. The young sun's fierce, unshielded radiation and powerful stellar wind, combined with the immense energy of the Theia impact, brutally stripped this tenuous envelope away into space. Earth was left briefly bare, its surface an incandescent furnace venting residual heat into the cold, dark void. But the planet's atmospheric story had only just begun. A second, heavier atmosphere would soon begin to rise. Not a gift from the cosmos, but forged from the deep, fiery heart of the world itself. This second atmosphere was born of fire, a direct exhalation from the planet's core. As the surface magma slowly hardened into a fragile, embryonic crust, the heat and pressure within forced a constant, violent outgassing. Volcanoes, perhaps far vaster than any we know today, incessantly vomited the planet's trapped chemical bounty skyward. Enormous quantities of water vapor, coupled with dense clouds of carbon dioxide, nitrogen, and acrid sulfurous gases, choked the air. This was no gentle breath. It was a crushing, steam-laden shroud, utterly unbreathable, wrapping the young Earth in an inescapable, superheated greenhouse blanket. Within this inferno, locked as scalding vapor overhead, lay the raw material for our planet's future oceans. A planet-spanning cloud of water, ready to descend. But how did so much water gather on a world born of fire, in a region of the solar system too hot for ice? And that water is itself a genuine mystery. The second great question of this story. Earth coalesced in a hot, inner zone of the solar system, too warm for significant water ice to condense, yet today it is a blue planet. So, where did all that water come from? For decades, the leading explanation pointed to comets, icy wanderers from the solar system's frozen edge, bombarding the young Earth and delivering their precious cargo. But recent analysis complicates that simple picture. The precise ratio of heavy hydrogen, or deuterium, in most comets we've studied simply doesn't match the isotopic signature of Earth's oceans. The puzzle is real, and its true solution remains hotly debated. The emerging consensus, however, points to multiple sources, most notably water-rich asteroids. These carbonaceous chondrites, hailing from the cold, outer fringes of the asteroid belt, carry a deuterium signature that far better matches our planet's oceans than comets do. Beyond impacts, a significant portion of water may have been locked away in the dust that first accreted into Earth, chemically bound within minerals, then later expelled by sustained volcanic outgassing from the cooling mantle. Even the primal solar nebula itself likely contributed a share of hydrogen. Earth's oceans, then, are not a singular delivery, but a complex cocktail. A blend of ice, gas, and rock, meticulously assembled over tens of millions of years. But however it arrived, this colossal volume of water remained trapped. It hovered, invisible, in a dense, scalding sky, waiting for a world cool enough to let it fall. And fall it would not for a very long time. Throughout the early Hadean, the surface stayed savagely hostile, vast swathes of fresh crust, constantly reworked by volcanic eruptions and residual heat from impacts, kept surface temperatures well over 200 degrees Celsius. Any liquid water was simply impossible. The thick, volcanic atmosphere then spiraled into a self-reinforcing furnace. This colossal blanket of water vapor, carbon dioxide, and other greenhouse gases efficiently absorbed and re-radiated the planet's heat back to the surface. This immense trapped energy prevented condensation, while the ever-present vapor only intensified the greenhouse effect. It was a planetary stalemate, a thermal prison, its own chemistry locking Earth into a perpetual state of boiling heat. Earth's blue future, its oceans, hung suspended overhead, waiting for a break in this inferno. For true oceans to be born, that self-reinforcing furnace first had to shatter. Slowly, over hundreds of millions of years. It did. As the great impacts subsided and the planet radiated its heat into space, surface temperatures crept downward. Yet, the crushing weight of that dense carbon dioxide atmosphere, by some estimates dozens of times today's, created a strange paradox. Water could remain liquid, even at scalding temperatures exceeding 200 degrees Celsius. This meant a searing proto-sea may have pooled on the early crust, a hot, heavy liquid world beneath an oppressive, vapor-laden sky. Whatever the precise sequence, the planet was poised at a fundamental threshold no world had yet crossed: the first true rain. There is a deep puzzle hidden in that cooling, and it runs in the opposite direction to everything you might expect. The young sun was not the star we see today. Physics tells us that 4 billion years ago it shone with only about 70% of its current brightness. A dimmer, cooler sun. By rights, The early Earth should have been a frozen ball of ice, its infant oceans locked solid. Yet the geological evidence says the opposite. There was liquid water, and plenty of it. Scientists call this the faint young sun paradox, and the leading resolution is the very atmosphere that made the place so hellish. That thick shroud of carbon dioxide and other greenhouse gases trapped heat so efficiently that it more than compensated for the feeble sun, keeping the surface not just liquid, but scalding. In other words, the same suffocating air that would have killed anything alive is probably the reason the oceans existed at all. It is a recurring theme in this story. On the early Earth, the difference between a hell and a cradle is often razor thin. When that oppressive atmosphere finally cooled past the critical point, the sky broke. The colossal load of suspended water vapor began to condense, and it fell, not as a passing shower, but as a deluge that may have lasted centuries, drowning the young crust and filling every basin on a still raw world. From a planet of ceaseless fire and scalding steam, the first oceans were born. Picture that rain. A downpour lasting not hours, but perhaps thousands of years, hot and relentless, thundering onto crust, barely cool enough to receive it, hissing into steam where it struck the hottest ground, pooling and flashing and pooling again, until, at last, standing water covered the world. There were no continents to shape a coastline yet. Only a global, shallow, storm-lashed sea over a barely solid floor. This was the single most transformative event in Earth's early history. The moment the planet turned, for the first time, toward blue. But proving such a momentous change occurred so astonishingly early would demand more than theory. It would demand physical evidence. A witness tough enough to outlast the destruction of its own world. And such a witness is desperately hard to find, because almost nothing survives from this age. Earth is a restless planet, its surface endlessly recycled by erosion and tectonics. Its original Hadean crust was ground up and remade long ago, leaving no intact Hadean rock anywhere on the planet to examine. Scientists needed something smaller and tougher than rock, a single mineral able to survive erosion, burial, melting, and recycling over and over for more than 4 billion years. But what object could possibly endure such an ordeal? That witness is Zircon. From the Jack Hills of Western Australia, geologists have meticulously recovered microscopic zircon crystals, fragments literally smaller than a grain of sand. These aren't rocks, but individual mineral grains, battered and re-cemented into much younger sandstone, yet preserved, dated to an astonishing 4 billion years old. They are the oldest physical traces of our planet ever found, genuine time capsules from the Hadean Eon. Their resilience is legendary. Zircons can survive unimaginable heat and pressure, resisting erosion, melting, and recycling far better than the bulk rock that once held them. It's why these microscopic grains are all that remain of Earth's earliest crust, bearing a silent chemical message about the alien world where they first crystallized. But how can anyone know a grain is 4 billion years old? The answer is a clock built into the crystal itself. When a zircon forms, its structure readily traps atoms of uranium but rejects lead. Uranium is radioactive. It decays into lead at a rate so precise it has not measurably changed in the age of the universe. So every atom of lead now sitting inside an ancient zircon is a uranium atom that has since decayed. And by measuring the exact ratio of the two, atom by atom, geologists read the time elapsed since the crystal formed, like counting the ticks of a clock that started 4.5 billion years ago. Two separate uranium isotopes decay at different rates inside the same grain, giving two independent clocks that must agree. A built-in check against error. This is not guesswork. It is one of the most rigorously tested measurements in all of science. And it is what lets us speak of 4 billion years and mean it. That message is nothing less than startling. The oxygen isotope chemistry, locked within these oldest Jack Hill's zircons, speaks of their formation from magma that had intimately interacted with liquid water at or near the planet's surface. This means liquid water, and a solid crust beneath it existed on Earth as far back as 4 billion years ago, pushing the timing of our planet's first oceans, and solid ground back by hundreds of millions of years, far earlier than scientists once imagined. This forms the cornerstone of the cool early Earth hypothesis, the idea that the Hadean Eon, between its colossal impacts, was not a continuous hellscape, but could host oceans and even early continents. This chemical echo from the deep past offers the boldest possible answer to the question of Earth's first water and land. Yet, honesty demands a crucial caveat. The zircons, astonishing as they are, offer an inference from chemistry, not a definitive visual record. While they indicate liquid water and a solid crust existed this early, they do not prove that world was consistently mild, or that oceans were global and permanent. The cool early Earth remains a leading interpretation, not a universally settled fact. With some researchers still reading these same ancient crystals more cautiously. What the zircons do establish, however, beyond any reasonable doubt, is that the raw ingredients of the world we know, liquid water and fragments of continental crust, were present astonishingly close to the planet's violent birth. The profound question, then, is no longer if solid ground emerged, but how these scattered first patches of crust could possibly grow into the continents we inhabit today. The how begins with a special kind of rock. The zircons hinted not just at any solid surface, but at something more specific: continental crust. Rich in lighter elements like silica and aluminum, this rock is inherently buoyant. That buoyancy is everything. Unlike the dense basalt of the ocean floor, which is constantly dragged down and recycled by the mantle, continental crust floats. It resists subduction, remaining at the surface, accumulating, enduring. These first durable, lightweight patches, once stabilized, are what geologists call cratons. They were the primordial seeds, the building blocks, of every landmass that would ever exist. Yet how these first cratons actually formed is a real and unresolved problem. The powerful engine that builds continents today, plate tectonics, with its grinding, recycling subduction zones, may not have operated on the young Earth at all, or not in the same way. Many researchers argue the Hadean and early Archean mantle was far hotter, making the crust behave differently. Softer, more mobile, perhaps like a lid that dripped and foundered rather than sliding plates. The exact timing of when modern-style plate tectonics switched on is one of the most actively debated questions in Earth science. Without that familiar mechanism, the true origin of these primordial landmasses requires a different explanation. Instead, one leading alternative points downward to the mantle. Towering plumes of superheated rock may have risen from deep within the Earth, partially melting the overlying crust and brewing the first buoyant, granite-like continental material from below. In this picture, the earliest continents were not scraped together at plate margins, but cooked upward by the planet's own internal heat, welling up as volcanic plateaus that thickened and stabilized over time. Whether by plumes, by early subduction, or by some combination, the first stable land began, slowly, to accumulate. But where can we actually touch those first fragments of ground? Where is the tangible proof of such an ancient, contested genesis? For the oldest surviving rock we actually stand on, we travel to southwestern Greenland, to the Isua Greenstone Belt. This extraordinary outcrop between 7 and 3, 8 billion years old, represents the largest exposure of well-preserved Eoarchean crust on the planet. To reach it, scientists brave remote terrain, often by helicopter, to find a landscape unlike any other. Here, the rock records tell a visceral story of our nascent world. Pillow lavas, contorted into unmistakable shapes, speak of ancient underwater volcanism, of magma cooling instantly in boiling seas. Banded iron formations, stark stripes of red and gray, suggest early chemical reactions between an iron-rich ocean and the scant oxygen present. And crucially, layers of metamorphosed sediments, ancient mud and sand, point to a dynamic surface. This belt, battered, folded, and cooked by later mountain-building events, nonetheless preserves rare windows onto the primordial crust we can still touch. Those banded iron formations deserve a closer look, because they are a portrait of an ocean utterly unlike ours. The early seas were rich in dissolved iron, held in solution because the water and air carried almost no free oxygen to rust it out. The iron stayed invisible, dissolved, for hundreds of millions of years. Then, in rhythmic pulses, something oxidized it, and the iron precipitated to the seafloor as fine rusty layers, stacking up into the striped rock we find today. Those stripes are a chemical diary of a planet on the verge of one of the greatest changes in its history. Because whatever was producing that oxygen in fitful bursts would, more than 1 billion years later, transform the world completely. Around 4 billion years ago, in what is called the Great Oxygenation Event, oxygen-producing microbes finally flooded the atmosphere with the gas, rusting the continents, poisoning much of the existing life, and setting the stage for everything that breathes today. The barren gray world we are describing was already quietly manufacturing the air we would one day need. But the Isua rock contains far more than the story of iron and air. Isua carries more than rock. It carries the whisper of environments. Some of its layers are metamorphosed sediments, ancient mud and sand laid down in water, meaning that by 7 billion years ago, there was already emergent land being eroded. Rivers or currents transported these grains, and standing water collected them, establishing solid ground and dynamic water. Nearby, on Aquileia Island, rocks dated to 85 billion years old have been argued to be among the oldest sediments of all, though this remains debated. Together, Isua and Aquileia reveal a world that, in the early Archean, had crossed a crucial threshold. It had true continents, running water, and the beginnings of a rock cycle, continually remaking its surface. But these ancient stones hide an even deeper mystery within their scarred depths. These same rocks sit at the heart of an even bigger question: when did life begin? Isua and Aquileia have both yielded proposed traces of it. In 2016, researchers reported structures in Isua they interpreted as 7-billion-year-old stromatolites, layered mounds built by microbial mats, which, if confirmed, would make them among the oldest undisputed signs of life on Earth. Aquileia's ancient carbon has been read the same way, hinting at biological activity. But both claims are fiercely contested. A later study argued the Isua structures are simply deformed rock, not fossils, and Aquileia's carbon signatures could have purely non-biological explanations. The question of life's true beginning brushes right up against the origin of land, and neither is settled. Yet, beyond the fierce debates, the broad picture becomes clearer. Across the Archean Eon, the scattered cratons grew, thickened, and finally stabilized. By roughly 3 billion years ago, enough buoyant continental crust had accumulated to form substantial, permanent land, a true milestone for the planet. This was not the vibrant green world we know. Instead, a scattering of barren gray shields broke the surface of an endless ocean, lifeless yet enduring. These were the proto-continents, and the very cratons that stabilized in this primordial era still form the ancient, indestructible hearts of our modern continents, hidden deep beneath younger rock on every inhabited landmass. But these new lands would not stay fixed. They were only just beginning their long, slow dance across the globe. These new lands did not stay fixed. Instead, these emerging cratons began to collide, forming the first tentative supercontinents. The earliest proposed is Valbara, a colossal amalgamation argued to have formed between 1 billion years ago. It linked two ancient surviving cores, the Kapval Craton in southern Africa and the Pilbara Craton in western Australia, the very Pilbara region that guards some of the planet's oldest undisputed fossils. Reconstructing Valbara is a profound act of planetary archaeology. Scientists match identical rock sequences and magnetic signatures, frozen into stone on continents now separated by thousands of kilometers of ocean. This detective work reveals a world where vast stretches of early land were already aggregating. Yet even as Valbara solidified, other colossal landmasses were emerging from the primordial churn. Another candidate for an early continent is dated to roughly 1 billion years ago. Some researchers have suggested that may, for a time, have been the largest continent on Earth, perhaps even something close to the only substantial one. It presents a haunting image, a solitary, gray island continent, utterly silent, adrift in a planet-wide ocean under an alien sky, with nothing living upon it. Fragments of are thought to survive today, in parts of India, Madagascar, and Australia. Yet the forces building these primordial lands would soon forge something even grander. Around 7 billion years ago, this process reached a new scale with Kennerland, one of the planet's first true supercontinents. It assembled through the collision and accretion of many older cratons and freshly minted crust, welding together vast blocks. These ancient fragments would eventually break apart, but their deep cores survive today as the foundations of North America and Greenland, Scandinavia, Western Australia, and Southern Africa. With Kennerland, the slow, relentless machinery of continental drift, as assembling, breaking, and reassembling supercontinents in immense, repeating cycles, was fully underway, a deep rhythm the Earth still keeps. Yet, to imagine standing on this immense, ancient land is to confront a world fundamentally unlike our own. Standing on that gray ground, you would find no soil beneath your feet. Soil, as we know it, is woven by life, and here almost nothing lived. No roots anchored the bedrock. Erosion, unchecked, carved rivers that braided in shifting sheets across bare stone. The air was a crushing, unbreathable shroud, thick with carbon dioxide and entirely devoid of the oxygen that defines our sky. Overhead, the moon hung far closer, far larger, raising monstrous, unceasing tides across the hot, empty seas. And the days themselves were brief, a handful of hours, for the young Earth spun at a furious, dizzying pace. This was Earth, yes, but it was an alien planet. And yet, this brutal, silent, world forged in fire and steam held within it the essential elements, the very foundations for everything that would come. And every part of that alien world was the necessary foundation for ours. The buoyant cratons offered stable platforms against relentless geological churn, eroding to shed crucial minerals into the seas, nutrients vital for nascent life. The primordial oceans were a universal solvent, facilitating complex chemical interactions for early biology. The crushing carbon-rich atmosphere held carbon and nitrogen compounds that living chemistry would later seize. Even the barren land played its part. Weathering of fresh rock drew carbon dioxide from the air, nudging the climate toward habitability. Nothing about the modern Earth would exist without this desolate apprenticeship of fire, water, and stone. And we know how easily it could have gone otherwise, because we can see the alternatives from here. Venus, our nearly identical twin in size and composition, almost certainly had water early on, and lost it. Sitting closer to the sun, its oceans boiled into the sky. The greenhouse effect ran away unchecked, and today its surface is hot enough to melt lead beneath a crushing, bone-dry atmosphere. Mars went the other way, smaller and colder. It once had rivers and lakes, but it lacked the mass to hold onto its air and warmth, and its water froze and bled away into space, leaving a rusted desert. Earth threaded the needle between them, far enough from the sun to keep its water, large enough to hold its atmosphere, and, crucially, geologically alive. Its continents and its churning interior became a planetary thermostat, drawing down carbon dioxide through the weathering of rock and recycling it through volcanoes, holding the climate over billions of years within the narrow band where liquid water survives. The first gray cratons were not just the seeds of land, they were part of the machinery that kept this world from becoming another Venus or another Mars. So, what did that primal world look like before the oceans turned blue? The answer to our opening question, what Earth looked like before the oceans, is a primal world of stark, successive transformations. From an incandescent liquid orb, it slowly congealed into a brutal, steaming furnace beneath a suffocating sky. Then, as the planet bled its heat, it revealed the first tentative gray islands of rock, solid ground rising above a hot alien ocean. This improbable progression, from fire to steam to water to enduring stone, forged the very conditions for everything that followed. These were the essential twin foundations on which the planet's entire future, its climate systems, its biological cradle, and eventually every living thing, including us, would be built. Even with these profound insights, the most remarkable part is how much of this remains open. The exact chemistry of the water's arrival, the precise moment the skies broke and the first oceans formed, when truly modern plate tectonics stirred to life, whether the cool early Earth truly offered periods of mildness, or if life had already taken hold in that primordial mud. Every one of these fundamental questions is still argued over, fiercely, in scientific journals. Each new Zircon crystal unearthed, each battered outcrop in Greenland, can dramatically shift our entire understanding, forcing researchers to recalculate timelines and redraw the planet's earliest maps. We are, quite literally, reading the deepest chapter of our world's story from a handful of surviving sentences. Etched in fragments older than any mountain, that we can reconstruct this alien planet at all from such sparse and indirect clues is a singular triumph of patient, relentless scientific inquiry. This painstaking work means that the next time you stand on solid ground, you might imagine the invisible journey of the rock beneath your feet. It could trace its ancestry directly to one of those first gray cratons, forged billions of years ago in a world without oceans, without soil, without a single living thing. This is our 4-billion-year inheritance, a direct lineage from a planet still forming itself. The story of the first continent is, in essence, the profound story of how a ball of primordial fire slowly, violently became a home.